The next talk is on a Codebert-based empirical framework for evaluating
Hello.
classification-enabled vulnerability prediction models. And the speaker is Tumu Akshar. He's from BITS, Hyderabad.
Good morning, everyone. My name is Tumu Akshar. I am an undergraduate student from BITS Pilani Hyderabad campus, and I am pursuing computer science. So today I am here to present our paper, uh, a Codebert-based empirical framework for evaluating classification-enabled vulnerability prediction models. So I have worked on this work along with my co-authors, Dr. Kumar, Dr. Vikram Singh, Dr. N.L. Bhanu, and Dr. Aneesh Krishna. So I have constructed my presentation as follows. So I'll first introduce the problem statement and what we want to achieve in this work, and then a little bit of related work to give you a flavor of the work that has happened in vulnerability detection so far. And then the study design, where I explain all the techniques that we have used for our comparative analysis, the empirical research framework to summarize the design, the experimental results and analysis, along with a comparative analysis of the techniques that we used using box plots and the statistical tests, and that will be followed by the conclusion and the selected references. So starting off, as we all know, software vulnerability detection is a pressing problem in both the software engineering and the cybersecurity domains. The reason is that vulnerabilities in the code leave the code vulnerable to major data breaches or for the compromise of the entire system. And if we build systems to detect these vulnerabilities early, then this might save organizations a lot of time as well as money and resources in fixing them. So as I said, the escalating number of disclosed security vulnerabilities has become a significant concern in these industries. And earlier, statistical tools, hard-coded tools, or manual tools were being used to address this problem. But the thing is, with the ever-growing code bases and also the sheer size of the code bases, this manual approach becomes simply infeasible in today's time. So with the proliferation of open source software, multiple data sets that we have or multiple codes that are available open source, this has resulted in the availability of vast code bases, and this has also given us an opportunity to enable to apply machine learning and deep learning techniques to leverage the patterns within this software codes and to build automatic vulnerability detection systems. So existing state-of-the-art works using deep learning and machine learning, they employ large language models such as BERT, GPT, and also pre-trained multimodal models, which have been pre-trained on natural language and programming language, such as Codebert. These have been used for encoding the code snippets and also detecting vulnerabilities in the code. But however, an issue with all the existing works, like all the state-of-the-art works, is they rely on fine-tuning the code. And as all the multiple authors discussed yesterday in the sessions also, fine-tuning the code can be a computationally expensive process. And with the ever-growing code bases, that might not be a feasible option that we keep fine-tuning the code every time the code base keeps growing. So in this work, what we want to do is, we want to combine pre-trained Codebert embeddings, where we take the pre-trained Codebert model and then we augment them with some easily deployable machine learning algorithms and data pre-processing techniques to give us computationally efficient models. Like, since these models won't involve the tuning of the Codebert model and will only involve training the model using these simple machine learning and data pre-processing techniques, this will give us a computationally feasible option and will also a computationally feasible option for the organizations to deploy these kind of models. So in this paper, our primary objective was to analyze the efficiency of pre-trained Codebert embeddings. We want to test whether these pre-trained Codebert embeddings can effectively capture the vulnerabilities in source code without any fine tuning, and can they provide efficient vulnerability detection models when combined with classification techniques. So after working on this, we also went a step ahead and we performed a comparative analysis of the different pipelines that we developed using various machine learning algorithms and the data pre-processing techniques. And we used statistical tests to find out which one could be the best among them. So we relied on standard machine learning algorithms and pre-processing techniques that have been used in the literature. The primary aim was to test the effectiveness of these pre-trained Codebert embeddings in the best manner, to see if they are capable for the task at hand. So I will walk us through the related works for a little bit. So Starting off with these automatic models that were built using machine learning and deep learning techniques, the first step in these automatic models would be to encode the source code, give us a numeric representation of the source code so that the other models can work on it and classify. So the works first started with using software code metrics. Software code metrics, basically they capture the syntactic structure of the code, and they also are a way to qualify and quantify the complexity present in the code. And as it has been proven in a lot of literature, these code metrics are very much correlated with the presence of vulnerabilities in the code. So I'll just give a couple of examples. So Medeiros et al., they experimented with different combinations of code metrics, and they relied on machine learning algorithms such as SVM and tree-based ensembling algorithms to test the efficiency of code metrics for the vulnerability code detection task. And Zagane et al., they also used code metrics. They generated code metrics for various code slices in the code and passed them to a deep neural network to detect vulnerable code slices, to classify which one of them are vulnerable and which one of them are not. So along with after software code metric based methods, the literature also moved a little bit simultaneously covered neural network based models, where the neural networks were used to encode the code snippets, encode the source code instead of software code metrics. So one example in this would be the work of Bhanu et al. So they converted the source code into abstract syntax tree representation, and then they used a bi-LSTM model to learn the high-level features from these ASTs that have been generated. And based on these features, they again applied machine learning algorithms and tree-based ensembles, SVM, KNN, different kinds of the standard machine learning algorithms to test the efficiency of these methods. So moving on, along with using deep neural network, a CNN or an LSTM from scratch, what other works did is they relied on deep source code embeddings, the pre-trained code embeddings that we have, such as Word2Vec, Glow, which have already been trained on lakhs of documents, and they already have some syntax, they already captured some syntactic and semantic structure of the tokens. So Wachinsky and et al., they used LSTM, they first took the Word2Vec embeddings, and they used an LSTM to refine the embeddings to get more mature features. And then they modeled a two-layer neural network for predicting the vulnerable code snippets. And after all these, the literature, the work moved towards large language models, and this is where we got the state-of-the-art results for this work. So I'll give a couple of examples. So Kim et al., they introduced the Waldebert model, which involved fine-tuning BERT over code gadgets generated from code slices to learn the contextual embeddings and then to detect vulnerable codes. And also Codebert has also been used in this work, fine-tuned Codebert models. So if you look at it, Yuan et al., they fine-tuned Codebert to model a Codebert-based embedding solution. And they also compared this model with other techniques that we saw, the deep source code embeddings, the deep neural network-based method, software code metrics. They also concluded that a fine-tuned Codebert model performs better than these the other methods that we saw. So as I said, along with Yuan et al., a lot of other works, they rely on fine-tuned Codebert models. So we wanted to spur research in the direction of using pre-trained Codebert models. So this work focused on checking whether pre-trained Codebert models can also perform comparatively well when we compare with fine-tuned Codebert models. So moving to the study design, these are the experimental data sets that we use. So we used 3 data sets that were provided by Lin et al. In their work. And these data sets were drawn from 3 open source software projects, FFmpeg, libpng, and libtiff. So all these 3 projects consist of C code, so codes in the C programming language, and they consist of functions in the C programming language. So from all the 3 data sets, in total we obtained 330 vulnerable code functions and 6,000 non-vulnerable functions in total. And these functions were manually labeled by the authors. So if we look at the project-wise breakdown, FFmpeg consists of 96 vulnerable and 777 non-vulnerable functions. Similarly, libpng has 43 vulnerable and 499 non-vulnerable functions. And libtiff has 191 vulnerable and 4,921 non-vulnerable functions. So moving on, after we generate these data sets, we pass it to a Codebert model to generate source code embeddings. And as we know, a pre-trained Codebert model returns 768 dimensional vectors. Now, The thing is, all these 768 dimensional features might not be useful for the model. There might be redundancies present in the model. The correlations between few of the features must be very high. So training the model on all these features is just adding to the computational complexity without giving us any new information. So what we do is to optimize the feature set and discard any non-influential features or also generate new features. We use the following 5 feature selection techniques: rank sum test, cross correlation analysis, principal component analysis, Gini index, and a genetic algorithm. So moving on, as I showed you before, all the data sets in total consists of 330 vulnerable code snippets and about 6,000 non-vulnerable code snippets. So that gives us a 1:20 ratio of the data points in both the classes. So this problem, this shows a severe class imbalance problem that is present in these data sets. And training the model on these kind of data sets could give us biased models, where the model could only learn to predict the majority class all the time. So to avoid that, what we do is we employ the synthetic minority oversampling technique, the SMOT technique. So as I said, in the original data sets, there is a severe class imbalance problem. So the SMOT technique, it synthetically samples some data points of the minority class to equalize and balance the number of data points in both the classes. So this way we can get balanced classes and perform our tests better. So after generating the data in the best form possible, we rely on 15 machine learning classification algorithms, the standard algorithms that have been used in vulnerability detection and also in other related problems in the literature. So we have relied on 3 naive-based techniques: decision trees, logistic regression, k-nearest neighbors, support vector machines with 3 kernels: the linear kernel, polynomial kernel, and the radial basis function kernel. We also have relied on the bagging technique on these different classification models to also see if ensembling techniques provide any advantage over the regular classification techniques that we have. So we use bagging with KNN, naive Bayes, logistic regression, and decision trees. And then we also use a couple of tree-based ensembling techniques to see if they provide any better performance: random forest classifier and the extractees classifier. So as I said, this is a summary or a representation of the empirical research framework that we use for our work. So we take in the C program methods or the functions that we have from the data set. We tokenize those functions, and then we pass it to the Codebert model, which learns the source code embeddings from the functions as we see over here. And then we pass these source code embeddings that have been learned to the feature selection techniques to optimize the feature set that we have. And then we pass it to the SMOT technique to balance the number of data points in both the classes. And then we pass it to the classification techniques. We train the classification techniques on the data that we have generated. And based on that, these classification techniques classify whether a functional code snippet is a vulnerable code snippet or non-vulnerable. And based on the results that we get, we performed a comparative analysis to see which techniques are helping it and if Codebert is actually capable of performing vulnerability detection at a functional level. So these are the accuracy values that have been generated for the models. So these are the different techniques, the classification algorithms that we use. This is on the original data and the SMOT synthesized data. And these are the combination of the data sets and the feature selection techniques that we have. So if we look at some of the results, for example, the results for Gini index, we can see a lot of hundreds in the accuracy. So before I explain this, we use the 5-fold cross-validation method to generate the testing accuracies that we are seeing right now. So for the Gini index, we can see a lot of hundreds in the performance, and also the genetic algorithm seems to perform well with a few hundreds, the 100% test accuracies. This is the case. And if we look at it on a high level, SMOT also, it follows the same method. Gini index and the genetic algorithms are giving better results, with Gini index having a lot of hundreds. And the performances for SMOT models is also a little higher than the original database models. So the average accuracy that we got over all the models that we developed 540 classification pipelines in total. So the average accuracy that we got was 92.22%, with the range from 48% to 100%. So moving on to the AUC values. So for all our tests, we considered AUC as our primary metric for the box plot analysis and also for statistical tests, because it is robust to class imbalance and it is also robust to the class distribution that we have. So since our model data consists of class imbalance, we relied on AUC metrics for our final analysis. So if we look at the values, again, we can see the Gini index methods and the genetic algorithms, they give us good results. And if we see for the Gini index, all the models have achieved an AUC of value 1. And this is also the same case with SMOT. All the values have been achieved 1, and we can also see ones in other places of the models along with a few in genetic algorithms. So the average, the range of AUC values that we achieved was from 0.37 to 1 with an average AUC value of 0.9. So to answer the first question, whether Codebert actually, whether the Codebert model, the pre-trained Codebert model is actually efficient for functional level vulnerability detection. As I told you, we have achieved an average AUC value of 0.9. And if you look at the basic comparative literature analysis of the AUC values, it says that an AUC value of 0.5 is just for a random classifier. And if you want to have a model which is capable of classifying something, it is between 0.7 to 0.8. 0.8, 0.9 is performed the good, is considered the good values for performer classification, and this is the desired value. And anything above or greater than or above 0.9 is considered excellent in case of classification. So as I told you, we achieved an average AUC value of 0.9, and this shows that on an average, Codebert is performing, the pre-trained Codebert model is performing excellently when we look at the task of vulnerability detection at functional level. So moving further, we also performed a comparative analysis of the different feature selection techniques, whether the SMOT technique is actually useful or not for improving the performance of the model, and the 15 classification algorithms that we have. So we first use the box plots to just get an observation or a representation analysis of how the model is doing for different techniques. And as we can see over here, we can actually get a pretty good picture from the box plots for the feature selection techniques. And as we can see for the AUC value, also for accuracy and the F measures, the Gini index method is performing the best with a very highly placed box plot. And also genetic algorithm seems to be performing better compared to the original set of features that we have, the rank sum test, cross correlation analysis, and PCA. And PCA somewhat seems to be lagging behind compared to the other techniques that we have at hand. So the box plot representation was only for an observational analysis, because we can't, there might be many cases in which the box plots are placed very close to each other, and we can't conclude which technique is the best performing among these. So for that, we relied on two statistical tests, the pairwise rank sum test and the Friedman test results, to see which model or which technique can we say is statistically performing better compared to the other techniques. So the pairwise rank sum test is basically a non-parametric test where we apply it on different pairs of techniques that we have the models, and for each pair, we have set the threshold value of 0.05 for the technique, and for each of the pairs of techniques that we have, this test says basically if the value is less than 0.05, it means that the performance of the model trained using both these techniques is statistically significantly different. And if the value is greater than 0.05, we can't say that, they might be similar. And the Friedman test is also a non-parametric test which we performed with threshold value of 0.05. So the Friedman test basically tests the null hypothesis, which says the performance or the different samples that we have, the performance of the models trained using different techniques, their performance does not differ statistically. And the alternate hypothesis is that the performance of the models trained using the different techniques is statistically different. So now if we, and for the Friedman mean rank, the lower the rank for a test, the better performing technique it is. So if we look at the rank sum results, as we saw from the box plots, we could say the Gini index and the genetic algorithms are the better performing models. And if we look at the pairwise rank sums for Gini index with corresponding to all other techniques, it shows a value of 0, which actually says the performance of Gini is statistically significantly different compared to other techniques. It is also the case with genetic algorithms. So to confirm our result that Gini index might be the best performing technique, we rely on the Friedman mean rank results. And as we see for the AUC metric, the Gini index technique only has a rank of 1.48, which is the least among all the other techniques. So this helps us conclude that Gini index is actually the best performing feature selection technique, which will help the Codebert model best bring out its ability to classify vulnerable code snippets. And after Gini, we see genetic algorithm is also performing well. And an important point to notice, the Gini index is performing much better than the model consisting of all the features. So we can say feature selection techniques, if we choose the right one, is actually helping the performance of the Codebert model compared to if we train the model using all the 768 features that we have. Now moving on to the analysis of the class balancing technique, the SMOT technique. In this section, we actually want to verify if SMOT is actually giving any performance benefit for the code-based models compared to if we use the original class imbalance data. So if we look at the box plot for the AUC value, the SMOT box plot is placed much higher compared to the original data. So this gives us a hint that maybe on an average, the SMOT model might be performing better than the original data. This is also the case for the F measure. And this might not be the case for accuracy because as we all know, accuracy is not the reliable metric in the presence of class imbalance data. So to confirm whether SMOT is performing better in a statistical manner, we again rely on the rank sum test and the Friedman mean rank test. So as we can see, the SMOT model and the model trained on original data, their performance is statistically different as shown by a value, rank sum value less than 0.05. And when we confirm it using the Friedman mean rank, the first column is for the original data and the second column is for the models based on this SMOT synthesized data. We can see that the AUC rank of SMOT is much lesser compared to the original data, 1.11 against the 1.89 of the original data. So this statistical test helps us confirm that SMOT is actually the better, actually improves the performance of the Codebert models. So moving on, these are the box plots for the 15 classification techniques that we have used. And this is the box plot for accuracy, AUC, and the F measure. So as we see over here, the box plots are actually not very concludable because a lot of techniques, for example, logistic regression, the support vectors, the tree-based ensembling, all of them seem to be performing well. So in this case, we rely on the statistical test to see which techniques actually perform better compared to the others. So these are the pairwise rank sums. So it's tough to go through all these models, but I can tell you the techniques such as logistic regression, the support vectors, and the ensembling. So these are not exactly statistically different compared to the other techniques among these. So as indicated by rank sum values greater than 0.5. So we rely on the Friedman mean rank test. And if you look at the mean rank values for AUC, we can see that logistic regression is having the least rank among all the techniques, followed by the support vector techniques, 4.94, 4.86, and 5.31. So based on this, we can conclude that logistic regression is actually performing best in bringing out the true potential of the pre-trained Codebert model for vulnerability detection, followed by the support vector machine techniques. So this is just a conclusion and a summary of all the results observations that we have seen so far. So we have concluded the pre-trained Codebert-based pipelines actually display a high predictive ability of vulnerable codes, vulnerable functions when trained using the right combination of ML techniques. And as I've explained before, these pipelines are much more computationally efficient compared to regular deep learning based models where we pre-train or where we fine-tune or train the model. So moving on, the feature selection technique of Gini index best improves the performance of the models and it also reduces the complexity of the model, thus giving us two benefits. And oversampling using SMOT effectively solves the class imbalance problem as it both improves the performance and the reliability of the prediction models, as we have seen from the statistics of AUC. And logistic regression shows the best predictive ability for the pre-trained source code embeddings for detecting the vulnerable functions, followed by the support vector machine algorithms. So these are some of the selected references for this work. And this was the work that provided us with the data sets that we used. So that's it from my side. Thank you. If you have any questions, please, you can ask.
Any questions? If there are no questions, so I mean, finally, what's the improvement over the baseline pre-trained Codebert? What's the percentage of improvement in terms of for the accuracy improvement?
That is not actually what we looked at, ma'am. So the baseline pre-trained Codebert, we just wanted to see if it is good enough to, if it is capable enough for giving us effective classification models. So we didn't use these techniques to see whether we can improve upon Codebert. We use these techniques to check whether we can bring out the true ability of Codebert in predicting the vulnerable snippets. That is why we relied on.
No, but the question is, if we are not bringing out the true ability of Codebert, Codebert itself is capable of classifying, right?
Yes,
what is the what is the improvement over the baseline?
We didn't check that for the pre-trained Codebert model.
And one more thing is, like when you're showing the improvement for each project, right?
Yes.
When you show accuracy of 1, which is surprising, the reason is
Yes, ma'am.
you're doing for per project.
Yes,
Usually
ma'am.
what happens is these models learn the tokens in the project, and it'll tend to repeat. Like the way to test this is you train on one
Cross.
model, one project, test it on the other project to actually see this out of vocabulary.
Yes, ma'am. That is actually the work we are working on, where we are testing it on the cross-project analysis, training it on one project and doing it on the other.
Actually, this
Yes,
one may not actually mean one. This
Yes,
very
ma'am. In that case, one may not actually be one.
Sure. Thanks.
Yes.